All right, in this video, I'm going to be working some improper integral examples and working through BC Homework 9.3. So 1a is the integral from 0 to 3 of 1 over 1 minus x squared dx. Okay. The issue with this one is where x is equal to 1, we're divided by 0, and 1 is in the interior of the region of integration. So what I have to do is I have to split this up into two separate integrals. So I know that this is going to be equal to the integral from 0 to 1. I might actually start writing this as 1 minus x to the negative 2 power, because I know that's how I'm going to need to anti-differentiate it, plus the integral from 1 to 3 of 1 minus x to the negative 2 power. And when you do this, I recommend working kind of like one of them and then the other one, not kind of like working them in parallel, because if one of them diverges, then the whole thing is going to diverge, and, you know, we'll be all right. So I'm going to anti-differentiate. So I'm going to add 1 to the power. I'm going to divide by the new power, but then I'm also going to have to consider the slope of the inside, right? Okay, so I think that this is going to be my antiderivative, because I'd have negative 1 minus x to the negative 2 power times the negative 1 for the chain rule will give me positive 1 minus x to the negative 2. And I'm going to let that run from 0 up to 1. And 1 is the troublesome point. And so I'm going to say that's going to be, I'm going to write it as a limit. Limit as the upper bound of integration approaches 1. Yes, in this case from the negative side, although it really doesn't matter, because it's to the negative first power 1 over 1 minus b minus 1 over 1 minus 0. This limit fails to exist, though, because as b approaches 1, I'm getting closer and closer to dividing by 0. So this fails to exist. So, I mean, I'll tell you, this is going to go the same way, because you're going to try to do the same thing with a lower bound of integration. It's going to fail to exist twice. If you've shown it fails to exist once, that's enough. And, well, there you go. I'm just going to say it does not exist or diverges. We could use that terminology as well. All right. 1b is the integral from negative 3 to 0 of 4 over the square root of x plus 3. That looks like cubed. I'm going to have to zoom in. Yeah, it's cubed. All right. And so I'm going to write this as 4 times x plus 3 to the negative 3 halves power. Okay, the half power from the square root, the 3 from the cubing. Okay. And the issue here is with negative 3. And you can see that the way it was written originally on the worksheet is, you know, you're going to be divided by 0 when x is negative 3. So that's the main issue. We're going to have to transform it into a limit. But first I can find an antiderivative. So I'm going to add 1 to the power. And then I'm going to divide by the new power, which would be like multiplying by negative 2. And I'm going to let that run from negative 3 to 0. What I might do is I might, actually just factor out that negative 8. So I'd say that's negative 8 times the limit as the lower bound goes towards negative 3. I guess from the positive side. Of 1 over the square root of x plus 3. Minus 1 over the square root of 0 plus 3. As a approaches negative 3 from the positive side, I'm getting closer and closer to dividing by 0. And so that means this limit does not exist. And I'm going to say that the integral diverges. Let's see, is x e to the negative 4x. How far? Yeah, there we go. And I'm going to look at this and be like, okay, I've got a product to my integrand. Nothing is the derivative of something else. I'm going to need to use UDV. So maybe I'll bring in some color here. Get my Yeah, there it is, my trusty blue pen. And I late algebra before exponential. So u equals x and dv equals e to the negative 4x dx. Take the derivative and the antiderivative. Okay, that would be e to the negative 4x. I'm going to have to divide by negative 4. So negative 4th e to the negative 4x. And then I need to remind myself that the integral of u dv from 1 to infinity is going to equal u times v from 1 to infinity minus the integral from 1 to infinity of v du. So this is going to equal u times v. So negative x over 4e to the 4x, I might write it like that, since I'm going to have to take the limit as x approaches infinity, minus the integral, so that'll be plus a fourth of v du, so plus 1/4 of the integral from 1 to infinity of e to the negative 4x dx. Okay. I'm going to say, well, that's the limit as b goes to infinity of negative b over 4e to the 4b. Okay, this is going to be bigger on bottom because exponential grows faster than first power of b. Minus negative 1 over 4e to the 4. Okay. There's that. And then plus 1/4 of, okay, well, when I anti-differentiate that, I'm going to get e to the negative 4x divided by negative 4. So I multiply by negative 4. And then it'd be e to the negative 4x, so e to the negative 4b minus e to the negative 4 times 1. Okay. Now what's going to happen here is b goes to infinity, this goes to 0. 0 plus 1 over 4e to the 4. And then I'll have minus 1/16 of, okay, e to the negative b, that's like 1 over e to the 4b. You know, e to the negative 4b is 1 over e to the 4b. As b goes to infinity, this is going to go to 0, and I'll have 0 minus e to the negative 4. And that's going to be a number that's suitable enough for us. Okay. Oh, D, this one's nice. This uses the thing that we just learned about last time. So the integral from 2 to infinity of 4 divided by x squared plus 4x plus 3. Okay, so we're looking at this. This is a fraction. It's not just a power of x. But I can see that I can factor the denominator. That means I need to hit this thing with partial fractions. So I'm going to go over here. I'm going to say 4 over, how does this factor? X plus 3, x plus 1. That's equal to some number over x plus 1 plus some other number over x plus 3. Okay, I'm going to clear out the denominator. And that's going to tell me that 4 equals a times x plus 3 plus b times x plus 1. Okay. When I let x equal negative 3, I get 4 equaling 0 and negative 2b. Okay, so that means b is negative 2. And when I let x equal negative 1, I get 4 equals 2a, which gives me a equals positive 2. So now I'm taking the integral from 2 to infinity of a is 2. A goes over x plus 1 minus 2 over x plus 3. Now I'm going to take an antiderivative. That would be, and maybe I'll factor out the 2 from this before I take the antiderivative. So it's 2 times log of the absolute value of x plus 1 minus log of the absolute value of x plus 3 as x runs from 2 to infinity. Oh, okay. This one, I told y'all you didn't need the log properties for this class, and that's probably still true, but in order to solve this problem, you're going to need to hit it with a log property, because otherwise it's going to look like infinity minus infinity, which is an indeterminate form that you would need to use L'Hopital's rule with, and it's like, I've got a video on that if you're interested. Search the channel for other indeterminate forms, or just search for L'Hopital's rule. But what I'm going to do is I'm going to actually scoot up a little bit. Actually, I'll try zooming. Yeah, so that you can see the whole problem. And I'll say that's equal to 2 times the natural log of x plus 1 over x plus 3's absolute value. Now, the absolute value won't really matter because I'm over here where x is definitely positive. But I'll do that as x runs from 2 up to infinity. Now, the step where I would plug in, that's where I need to transform to a limit. So that's 2 times the limit as b goes to infinity of the natural log of b plus 1 over b plus 3 minus the natural log of, when I plug in 2, I get 3/5. Okay. And let's think about what happens to this fraction as b goes to infinity, not the log. What happens to just the thing inside the parentheses as b goes to infinity? These are essentially the same, right? First power of b, we would divide the leading coefficients. This fraction gets closer and closer to 1. And if you think about it, like say it's 1,000. B is 1,000. You got 1,001 divided by 1,003. Those are really close. And 1,000,001 plus 1,000,003 is going to be even closer to 1. Okay, so the closer the b gets to infinity, the closer that fraction gets to 1. I'm taking the log of 1. We know that's 0. So I've got 2, well, I guess negative 2 times the natural log of 3/5. You might be thinking to yourself, wait a second, dude, like that original integral, it was the integral of a very positive function over, it was an integral of a function that was positive over this entire x interval from 2 to infinity. And so, shouldn't it be positive? But if you think about log of 3/5, that's a negative number multiplied by negative 2 is going to be a positive number. Okay, that was how we could mix partial fractions and improper integrals together. Next few should probably be a little faster, I would hope. The past few have involved a lot of steps. Okay. Integral from 1 to infinity of 3x plus 1 squared in the denominator. I might write that as the negative 2 power. I'm going to find an antiderivative. But then I also need to divide by the slope of the inside, right? Because that 3 is going to have, there's going to be some chain rule consequences there. So I think I'm going to divide by the new power and divide by that 3, so it would be negative 1/3. And this is one that you definitely want to check by taking the derivative. Negative 1/3, 3x plus 1 to the negative 2 power times 3 for the chain rule, then, okay, I'm back to this. As x runs from 1 to infinity. Okay. This is the limit as the upper bound goes towards infinity of, okay, maybe I call 3x plus 1 to the negative first power 1 over 3x plus 1. What is 3x plus 1? Oh, 3b plus 1. Can't just plug in infinity into a function. It doesn't work like that. Minus negative 1/3 of 1 over 3 plus 1. When I plug in x equals 1, that's 1/4. And so, as b goes to infinity, this fraction goes to 0. So I have 0 minus negative 1/12 is positive 1/12. F is the integral from, oh, that's nice, we haven't done any of these yet, negative infinity up to 0 of 1 over 2x minus 5. I'm going to anti-differentiate this thing. We have to be real careful because of that 2x right there. So this would be the natural log of the absolute value of 2x minus 5. But if I took the derivative to check myself, I'd have 1 over 2x minus 5 times 2 for the chain rule. But I only have times 1 for the chain rule. So, I guess not for the chain rule, but that's where I need to divide by 2 to prepare for that 2 coming out with the chain rule. So then I've got this running from negative infinity up to 0. So I'm going to turn this into a limit. The limit as the lower bound of integration approaches negative infinity. So I plug in 0, and I got half of the log of the absolute value of negative 5. That's fine, because you take the absolute value of negative 5, and that's 5, and that's something I can take the log of. All right. As a approaches negative infinity, this whole thing is going to approach negative infinity. The absolute value will approach positive infinity, and as you know, the argument of a log approaches positive infinity, the log itself needs to approach infinity as well. So I think I've got negative infinity, and that is going to, yeah, because 2x minus 5 is a negative number when x is negative. So this approaches negative infinity. We can say the limit fails to exist, and the integral diverges. What's the next one? Oh, yes. All right. Now this is something we have not seen in a while, but this is part of AP Calculus. And, you know, you need to be at least aware of it. Negative infinity up to 1 of 2 to the t dt. That's one that we need to know. Okay. So I've shown you why this is true in the past, and so I'm going to probably refrain from doing that. And instead, I'm just going to remind you of the formulas. The derivative with respect to u of some number to the u, that's equal to a to the u times the natural log of a. Okay? That even works when a is e, right? The derivative of e to the u is e to the u, but the log of e is 1. And then the antiderivative of a to the u with respect to u is going to be 1 over the natural log of a times a to the u. For reasons that I have gone through before, basically the way I like to show it, or to come to it, is you turn a into e to the log of a, and then you use the chain rule. Okay, and then over here, the same thing. E to the log of a, we'd have to divide by the slope, just like I was doing, you know, over here, and before. I've done it a couple times. So over here, if I'm equipped with this knowledge here, I can say, all right, well, I've got an antiderivative for 2 to the t. It's going to be 1 over the log of 2 times 2 to the t. I'll let that run from negative infinity to 0. And negative infinity is not something I'm going to be able to plug in, so I take the limit as the lower bound goes to negative infinity. Okay, lower bound, negative infinity. I'm not sure why I'm panicking here, but 1 over the log of 2. I might factor that out from both terms, because I didn't do it this time. I could have taken out that 1/2 there, but you know, you could do it later, or you could do it, you know, preemptively and have it outside the limit. It really doesn't matter. If you want to leave them in there, that's cool too. But I'm going to say 2 to the 0 minus 2 to the a. Now, as a approaches negative infinity, let's think about what's happening to 2 to the a. 2 to the negative 10 is 1 over 2 to the 10. It's already a pretty small number. Let me show you that. Okay, so 2 to the negative 10 is 9.76 times 10 to the negative 4. Okay, that's very small. Okay, and then 2 to the negative 100. Let's see, can it do that? Yeah, 10 to the negative 31st power. That's basically 0. Okay, or you could think of it as 1 over 2 to the a as a goes to positive infinity. However you like it. Either way, this thing approaches 0, so I've got 1 over log 2 times 1 minus 0, and that's just going to be 1 over the natural log of 2. The next one is the integral from 1 to infinity of 1 over e to the x dx, which I feel like might have also been in the notes book, but it's all right, we can do it again. we're going to rewrite this to anti-differentiate. We're going to rewrite it as e to the negative x, right? Right, as a negative power. One of our main techniques of dealing with fractions in the integrand, right? Especially if it's a simple fraction like 1 over e to the x or 1 over x to the third, something like that. Just write it as a negative power. Okay, we're going to anti-differentiate. Okay, it's e to the negative x divided by the negative 1 to prepare for the chain rule. We're going to let that run from 1 to infinity, and then at the stage where we would be plugging in, that's where we need to transform to a limit. That's the limit as b approaches infinity of, you know, right, negative e to the negative b minus negative e to the negative 1. Okay, me personally, I don't just look at this limit and be like, okay, I know it's going to go to 0. Maybe I do, but wouldn't expect you all to. I would say, all right, if I can't see what's going on here, I might say this is negative 1 over e to the b. And this fraction is pretty clearly going to 0 as b goes to infinity because the denominator just gets really big, plus 1 over e. Okay, this goes to 0. That doesn't care what happens to b, so this limit is 1 over e. Maybe that was slightly different from the, I think maybe, I don't remember. Just a couple hours ago that I did that, but it'll be all right. I is, all right, 1. I is going to be integral from 2 to 3 of 1 over the square root of 3 minus x dx. Did we? I feel like there's, no, let's see. Okay, I was thinking about a. Okay. No, not exactly the same. All right, so I'm going to start by rewriting as a negative power. Say that's the integral from 2 to 3 of 3 minus x to the negative half power. Okay, the trouble here is where we plug in 3, right? Is there's going to be a vertical asymptote at the right edge of my region of integration. So I just have to remember that 3, I can't just plug in on that. I'm going to have to take the limit as the upper bound approaches 3. Okay. Then, what am I going to anti-differentiate? Add 1 to the power, divide by the new power, but then also consider what's going to happen with the chain rule, right? If I took the derivative of this to try to make it get back to that, I'd have 1/2 times 2, that's good, that's 1, times this thing to the negative half, that's exactly what I have, but then I would have to multiply for my negative 1 for the chain rule. So I'm just going to prepare for that by dividing by negative 1. And then I'm going to let it go from 2 to 3. But 3, we really can't plug in 3 because this is an improper integral, right? This integral, just plugging in top and bottom is only defined when the integrand, the function we're integrating, is continuous over the entire region of integration. And when it's not, we have to transform it into a limit. So b is approaching 3 from the negative side of negative 2 square root of 3 minus b minus negative 2 square root of 3 minus 2. Okay. As b approaches 3 from the negative side, I'm getting closer and closer to taking the square root of 0, and we know what the square root of 0 is, that's 0. And so I've got 0 plus 2 times the square root of 1 is equal to 2. J is going to be the integral from, oh, this one's a little tricky. This one, you don't have to worry. If you don't see this immediately, I don't need you to worry about this until next time. That's when I'm going to need you to worry about recognizing this antiderivative. Okay, so this is the integral from 1/2 to 1 of the 1 over the square root of 1 minus x squared. Okay, this would be troublesome at 1, okay, because I'd be taking, the square root of 0 and dividing by 0. That's troublesome. But what we're going to do is we're going to look at this and be like, okay, that x squared, I can't just say this is 1 minus x squared to the negative half and add 1 to the power and divide by the new power. It's just not going to work out for us. Because of that x squared, there's chain rule consequences. This is an antiderivative we just need to know. This is this 1 over the square root of 1 minus x squared. That's the derivative of inverse sine of x, right? The derivative of arc sine. So I know that this is arc sine of x as x runs from 1/2 up to 1, but that 1 is troublesome because that's the reason it's an improper integral, so I'm going to take the limit as the upper bound goes towards 1 from the negative side of arc sine of b minus arc sine of 1/2. And now we're going to need to do some trigonometry here. All right. It's a good thing that b is approaching 1 from the negative side, because if it was approaching 1 from the positive side, it's like, where is sine, where on the unit circle is the sine of theta equal to 1.5? Well, never, right? It's never bigger than 1. So as we're approaching 1, right, in the sine world, theta is getting closer to this, right? Because sine of pi over 2 is equal to 1. Okay, that means that inverse sine of 1 is pi over 2. So that's pi over 2 minus arc sine of 1/2. Where is sine equal to 1/2? Well, about here. That's going to be at pi over 6. Okay, you can't see that, but I wrote it equal to half. And so that would be pi over 6. Okay, that would be a safe place for us to stop. Or you could say that the difference in a half and a third is a sixth, or the difference in a half and a sixth is a third. So you could also combine that and make pi over 3. Let's get some more. All right, K and L. I'll probably be able to do just those two in this sitting. And that's, I don't know, showing through. All showing through. Okay, let me get some better scrap paper. It's not going to be bell schedules or academic calendars. Right, perfect. Yeah, that'll be good. 1K. The integral from 0 to infinity of 1 over y squared plus 4y plus 4 dy. All right, we're looking at this and we can say, hey, I can factor this. Okay, this is going to factor to y plus 2 and y plus 2. And if we have a repeated factor in the denominator, we're just going to use the power rule. Okay, so I'm going to go over here and I'm going to say, this is the integral from 0 to infinity of 1 over y plus 2 squared. Okay, this could be troublesome if I was integrating from like negative 2 to 0 or something, because of the vertical asymptote. But that I'm not going to have to worry about that, because 0 to infinity, that doesn't include negative 2. So I'm never going to be dividing by 0 in my region of integration. What I have to worry about is at infinity, right? So I'm going to take the antiderivative. So that's y plus 2 to the negative 2 power. I'll even write that. dy. And I'm going to add 1 to the power. Divide by the new power, check to make sure it's a valid antiderivative. It is. And I'm going to let that run from 0 to infinity. I can't plug in infinity, so that's why I'm going to transform to a limit. And that's going to be the limit as my upper bound goes towards infinity of negative 1 over b plus 2 minus negative 1 over 0 plus 2. As b goes to infinity, this fraction is going to 0, so I'll end up with minus a negative half is positive 1/2. All right. 1L. This integral from negative infinity to infinity of x to the third times e to the negative x to the fourth. Okay. This is looking like u du, because the derivative of negative x to the fourth is proportional to x to the third. All right. Oh, okay. I don't know. Maybe this works, maybe it doesn't. This is going to be interesting. I'm not sure how this is going to go. I think I know what's going to happen here. So I'm going to let u equal negative x to the 4th. Okay? So that du is equal to negative 4x to the third dx. But I don't have negative 4x to the third dx. I just have x to the third dx. So I divide both sides by negative 4 and say x to the third dx equals negative 1/4 of du. And then I need to convert the bounds as well. As x approaches infinity, what's going to happen to u? U is negative x to the 4th. U is going to approach negative infinity. And then as x approaches negative infinity, we're taking a large negative number and taking it to the 4th power, okay, because exponents before multiplication in the PEMDAS world. Okay, that's a huge positive number when I take it to the 4th power, and then I make it negative. That means u is approaching negative infinity here as well. And so what this is going to be is this is going to be, okay, the x to the 3rd dx becomes negative 1/4 and du. I have e to the u. And this is x, as u goes from negative infinity to negative infinity. And I gotta think that that's going to be 0, right? Because the bounds are the same. Okay, whatever's going to happen, well, I guess, yeah, it's, okay. Provided that this limit exists, it's going to be equal to 0. So I'm going to go through and make sure that we're in agreement that the integral exists, but it's going to. So I get an antiderivative. I let the lower bound and the upper bound approach negative infinity. Okay. And, I mean, I guess since they're both approaching the same thing, we could, you know, say both cases. And again, that's kind of presuming it equals 0. So I guess I'll take the limit as both a and b go to negative infinity. And I'll have negative 1/4 of e to the b minus negative 1/4 of e to the a. Both of these limits are going to 0 because it's e to the negative infinity, or just basically 1 over e to the infinity. These are going to 0. Each 0 minus 0 is going to be 0. Okay, so this one did exist, and it did equal 0. I'm struggling to think of one where I'd be interested if this was, you know, negative x to the 3rd and x squared. I think that would play out differently, but I think that one would diverge. But yeah, because I didn't put that problem on there. I must have had a reason for it at the time. Okay, that was L. And how many more do we have? Just a few more. Got a class about to come in. I think I'm going to stop. I'm just going to stop here, and I'm going to record, you know, numbers 2 through 9 in a separate video. And so that'll be all for this one. Sure, I'll, you know, link the next one somewhere up here so that if you just wanted to, you know, click forward and watch the rest of the solutions, you can click there. But thanks for watching.